Hello everyone, welcome to the GeoEcologist. I am Dr. Krishnanand and you have been watching my videos on climatology and other sections of geography on my channel. So if you are new to this channel, do subscribe to our channel and check the playlist for yourself for the regular videos of geography. So in today's session on climatology, we are going to talk about the temperature and pressure belts. So how are these belts organized? What are the important features of these belts? And what is the basic understanding of these temperature and pressure belts in terms of climatology. So before we go ahead, don't forget to subscribe to our channel and also share the videos with others as well. So after we have learnt about solar insolation and temperature distributions on the horizontal earth surface, now let's learn about these temperature and pressure belts. So first of all, let's understand what are these various belts of temperatures and why are they called belts. What is the basic reason behind it? So remember, on Earth in tropics, this insolation comes very vertical, and as you go away from the tropics, it begins to slant. So what happens in specific regions on the Earth, there are specific kind of temperature conditions existing. So that's why these important regions are also referred to as belts, and they are marked by latitudes, as we see. So we also have learned latitudinal heat balance in the earlier lectures. So what you see here is all these belts right from equator to the pole. So what are these belts called? One is called the tropical zone or the tropical belt, as we know, right from equator to this tropics on both north and south. Then we have a temperate zone, and then we have a polar zone. So three major zones are there, which are also known by other names. So we are going to elaborate first on the temperature belts, and then we'll learn what are the pressure belts and how are they related. So the first belt that we'll learn is the torrid zone, and it is known as the hottest heat zone. And where is this torrid zone? This particular zone, that is the equatorial zone. This is called torrid zone. And remember, this is torrid zone because it receives maximum solar insolation. So it is the largest of the thermal zones. Now remember, we are learning here about the heat zones, about the temperature zones. So that is thermal in nature. So that is what we study here, is that it is the largest thermal zone on the Earth. And remember, this is the central part, right, along the equator. So what happens? Sun's rays are almost vertical here throughout the year, right? And midday sun is overhead at equator on equinoxes. Remember, we have learned in the latitudinal heat balance as well. So on 21st March and on 23rd September, sun shines overhead. It means it's completely vertical. So it is also overhead at Tropic of Cancer on 21st June and Capricorn on 22nd December. So if you see these lines, tropics, so vertical here as well and vertical here on equator as well, and that is why this entire zone, this entire belt receives maximum solar insolation and is the accumulation of lots of energy here. So the duration of day and night are always equal when we say equinoxes. Remember, 12 hours day, 12 hours night on equator, and they increase to 13 hours and 27 minutes at tropics. So that is how this fluctuation keep happening. And remember, if the day length is more, what does it mean? It means there is more recipient of energy, that is through insolation. So torrid zone basically lies between what? Tropic of Cancer and Tropic of Capricorn. So remember, Tropic of Capricorn is in the south and Tropic of Cancer is in the north. So this particular belt, this particular zone is called torrid zone. So northern torrid zone is between the equator and Tropic of Cancer, and southern torrid zone is between the equator and Tropic of Capricorn. So this is the first important zone which receives maximum accumulation of solar insolation that we know. So this is the hottest heat zone. Then the next subsequent zone after these tropics to this particular belt, that is Arctic Circle, this particular zone, this is known as the moderate temperature zone and also called temperate zone. So that is what is important here to learn, that equatorial or tropical zone, then we have a temperate zone, right? So temperate zones are moderate temperature zones, right? They do not receive this solar insolation in a vertical manner. There is a slanting. So because of this slanting, this energy, which is kind of a constant energy, we say as solar constant, now it is distributed over a larger area. So what happens? There is a mildness or moderateness in the temperature. So in summer, in the northern hemisphere, it is winter in the southern hemisphere. Remember, when it is summer in northern hemisphere, it means sun shines overhead this side. So where is winter? In southern hemisphere, and vice versa. This keeps happening. So there is also a change of what? Season, as we know, and the duration of night and days as well. So northern temperate zone, what we observe here is that it lies between Tropic of Cancer and Arctic Circle, that is 66.5 degree north, and southern temperate zone lies from Tropic of Capricorn to this Antarctic Circle, as we see, that is about 66.5 degrees south. So this zone is also known as mid-latitude zone and temperate zone, and it has a moderation here, right? It doesn't have maximum insolation because maximum insolation is only fixed to this equatorial or tropical zone. So that is important here. Now, the next important zone, as you see, as you go closer to this particular pole area, what do you see? It is called frigid zone or polar zone, and it is the coldest zone, obviously, right? Why? Because the energy is slanting over a larger area, not much of solar insolation is received. So what happens? Most of the areas are permanently frozen in this particular zone, right? It is the least heated zone. It is the coldest zone, that's why. And northern frigid zone extent is from 66.5, that is Arctic Circle, to the 90 degree, that is the North Pole. And southern, obviously, it is again from Antarctic to the South Pole, that is 90 degree. So this is the extent. Now these are the three major belts or zones of temperature, as we see. So maximum temperature, then moderate temperature, and then minimum temperature. So three major zones. Now, why is it important? Why are these temperature zones important? Because they regulate our climate. Remember, temperature or solar insolation, for that matter heat, is one of the major driving forces for all the atmospheric and climatological phenomena that we study. Because energy is one thing that keeps transferring from one place to the other, and along with it there are lots of changes happening subsequently. So that's why these temperature zones, these important tropical, temperate and polar zones are important for the climatology and for human beings to survive, to locate themselves on Earth. Habitable zones, remember, in ancient, right from ancient, the zones of habitability were also discussed historically by Parmenides and Aristotle in the ancient. And remember, all these zonations that we see, the climatic classification that we study in future lectures to come, all these things are driven by this important force, that is solar insolation, that is heat. And these are the major heat zones that we study, and we divide them into these three major zones. And that's why, remember, temperature zones on this Earth are important. So what we study is these three zones, these three belts, that is tropical, temperate and polar zone, also known as equatorial, that is torrid zone. Then we have moderate temperature zone, that is the temperate zone, and then we have the frigid zone. So that is the major classification of these temperature belts on the Earth's surface. Now let's look at the pressure systems. So what are the pressure systems all about? Now the air expands when heated. The entire basis of this pressure system is built on this thing. Again, you see here, heat is important. As we were discussing in the temperature belts, what we see, different belts, different zones on Earth gets heated differently. So what happens? What will happen if the heat is coming in a particular way? So it will heat the air in the atmosphere, right? So atmosphere, when heated up, what will happen to it? It will expand, it will get lighter, and it will move up. Remember, hot air rises up. So it will start a motion, it will start a movement, right? So it will either get expanded or it will get compressed depending upon heating or cooling. So hot air expands, cold air is compressed. It means when there is a system of air in which there is heat supply, what happens? The molecules go far away from each other, right? The kinetic energy principle. And then when it is cooled, right, when it is a cool system, then what happens? The molecules condense, they come together. So that is the entire principle of thermodynamics that we study. So this is behind this pressure system creation. So what happens? Because of this heating and cooling, there are variations in atmospheric pressure in different places on Earth. So these differences in atmospheric pressure causes movement of air from higher pressure to where? To the lower pressure, and that is important, and that is what sets the air in motion, and that is what also leads to this distribution of energy from this torrid zone to this polar zone across the temperate zone on Earth. And remember, that is how the heat is redistributed from the major belt to the minor belts on Earth, right? So that we have studied already in the previous lecture in latitudinal heat balance as well. So this is where we say wind is generated. The concept of wind comes from this idea that the pressure systems are created and then there is a dynamism involved, there is a movement involved. So air starts moving in horizontal way, which is called wind, right? And what is the function of this movement? It redistributes the entire energy. That is why it is important. It distributes the heat and moisture all across the latitudes, all across these temperature belts that we see, all across these pressure belts that we know, right? So we are going to look at these pressure systems and pressure belts, in what ways they exist, what are their major factors associated, and what are the important characteristics associated with these systems. So what we observe is that vertical rising of moist air forms clouds and bring precipitation. And remember, the entire climatic phenomena, right, from the insolation to precipitation, is now going on the entire earth. So this is how we study the major parameters of climate, through temperature, pressure, precipitation, all these variants that we know, right? So that is why the temperature belts alongside with the pressure belts or pressure systems are important for studying the climatology. So now let's look at this factor, that is air pressure. So basically what it is a force exerted in all directions by the air, right? By the air movement. So what happens? It is basically the weight of a column of air. When we say that if there is this particular column of air, it is having a weight. And remember, gravity is there, so it exerts a weight. So this particular air column, when it exerts that particular weight here, that is what we understand as atmospheric pressure. So this is what is atmosphere, that envelops the entire globe, and it exerts a given pressure on each and every point on the earth. That is what we remember as atmospheric pressure. And atmospheric pressure is the weight of column of air at any given place and time. That is the simplest definition. And how do we measure it? Remember Torricelli, in the first lecture we discussed what was the development in 18th century. So barometer was invented in 17th century by Torricelli to actually measure this pressure. And what is the unit? It is called MB. So remember, it is millibars. And how do we define 1 millibar? This is the statement here. 1 millibar is equal to the force of 1 gram on a square centimeter. So remember, in a square centimeter, 1 by 1, that is the square centimeter, 1 centimeter by 1 centimeter. This is the force applied. And remember, a pressure of 1000 millibars is equivalent to the weight of 1.053 kilograms per square centimeter. So this is about the measurements. In simplest way, if we measure it through mercury, what can we say? It will be equal to the weight of a column of mercury 75 centimeter high. So normal pressure, that is atmospheric pressure, that we remember we measure at the sea level, right? So at sea level, it is taken to be 76 centimeters of mercury column. So that is how we measure that pressure. Now we are looking further into vertical variation of this pressure, how this pressure changes with altitude or elevation. So remember, in the lower atmosphere, the pressure decreases rapidly with height. So in lower atmosphere means troposphere. Remember what happens? If we go up, the temperature also decreases. Remember, lapse rate. And when we say temperature decreases, right, what happens? There is also simultaneously decrease in pressure as well. And remember, at the height of Mount Everest, as we see, the air pressure is about 2/3 less than what is at the sea level. So this is the amount of difference that we are talking here. So vertical pressure gradient, remember when the word gradient is used, it is the degree of pressure or degree of measurement. That's why it is called gradient. So vertical pressure gradient force is much larger than the horizontal pressure gradient. So that is a thing to remember here, that vertical pressure gradient is larger than the horizontal pressure gradient. So it is generally balanced by nearly equal but opposite gravitational force. So remember, this pressure is balanced by the gravity force, and that is how it is kept in a balance on the earth. That's why, remember, we do not experience strong winds upwards, right? That is why it is a balance between the gravity as well as the vertical gradient force. So let's understand further more. Now, when we look at the horizontal distribution of the pressure through these pressure belts, remember, we have already learned about these temperature belts, right?
So accordingly, there is a difference in pressure belts as well, because temperature and pressure, they have a relationship. In the earlier lecture, we have also talked about the gas laws, remember? Boyle's law, Charles' law, Gay-Lussac's law. So that is important, right? So what happens? The various pressure belts on the earth have been divided into 7 particular belts. Now, why do I say 7? Because 1 is the equatorial belt, right? And apart from that, 3 on each side of the equator. So 3 plus 3, and that is 1 is equatorial belt, so it becomes total 7. So 1 is the equatorial belt. Then we have 2 subtropical highs. Remember, subtropical belt, that is near tropics, right? So this belt is subtropical in north and south. So these are 2 in number. Then we have 2 subpolar low belts, that is here near the poles, right, in both the hemispheres. So it is 2 in number. And then we have polar highs on both the sides. So we have 2 in number. So that is in total 7 pressure belts are there, right? So remember one more point, that except the equatorial low, all others form matching pairs in the northern and southern hemisphere. So remember, whenever we see the shape of the earth, right, we try and idealize into this image, which is here, right? A perfect image of a geoid. But actually earth has a variation on the surface. So if you look, the actual earth is like this, which is also called oblate spheroid, right? So largely, if we divide the earth into 2 parts, the equator is that particular line. So north of equator and south of equator, everything is matching, is equal in pairs, right? So we have 2 belts, each of them, right? Lows and highs, what we see here. So in total, what we have is 7 belts. So let's discuss their characteristics now. So first one is the equatorial low pressure belt, and which has a very important point that we remember is called doldrums. So what is the extent of this particular low pressure belt? This is the 10 degree north to 10 degrees south, right? And this zone is also known as the doldrums. Many places it is 0 to 5 degree north and south. So that is correct. That is a particular zone where there is an extreme calm air. So that reason is called doldrums. Now its width also keeps varying. Remember, this is because of the pressure changes. So the variation range is about 5 degree to 20 degree north and south. And this particular belt is also known as intertropical convergence zone, ITCZ. Why? Because there is a convergence happening of the winds from this northern side and this southern side here in this particular belt, right? As you remember, that heat is the driver of air. So when heat is received in this particular belt, hot air rises up, and to fill this gap, air rushes from both the sides. So this particular zone is the zone of convergence. And then that particular point, that is 0 to 5 or 10 degree north and south, that particular zone has an extreme calm movement of air, and that particular zone is known as doldrums as well. So the position of the belt varies with apparent movement of the sun. Remember, sun is northward vertical here and then southward vertical here, different in different seasons. So we have seasonal variation, remember? So that is important to remember in terms of the variation of this belt. So this belt is characterized by what? Now look here, extremely low pressure with calm conditions. Now this is a very significant point. It is extremely low pressure belt, but calm conditions are there. So this is to remember that there is an absence of a surface wind here. Since the wind approaching this belt begin to rise near its margin, thus only vertical currents are found. So what happens if you look into this image? Now let me clarify this once more. The winds of similar nature are coming here. So remember, the wind of this side and this side are actually coming together, but they have a similar nature. So when they meet, what happens? They go upward, and this particular zone remains calm because there is no surface wind, and that is why this calm area is known as doldrums, which doesn't have much of air movement only. Right? So that is the whole idea behind this equatorial low pressure belt and doldrums. Now, to understand the zones of doldrums on Earth, Crow, the scientist, has also discussed and divided this particular zones of doldrums that we need to know. So first is called Indo-Pacific doldrum. So if you look into this Pacific Ocean and Indian Ocean, this particular zone is known as the first doldrum belt. Then it has extension from the eastern coast of Africa to 180 degree longitude. Remember that particular 180 degree longitude which divides the time, right? So that is important, international date line. So that is the demarcation here for the first zone. Then the next one is the equatorial western coastal region of Africa. So this particular zone is also known as the doldrum. And then we have western coastal margin of Central America. And this is that particular zone that is called doldrum. So 3 doldrums have been identified on the world map that you can draw and practice for yourself. Now let's learn a little more about intertropical convergence zone. So this intertropical convergence zone is basically what? It's kind of meeting of 2 fronts. Generally, a convergence zone is talked when 2 different kinds of air fronts are meeting here. It means there is a front creation where there are 2 different kinds of air meeting. There is kind of a war. So we have a war front, like similarly. So fronts are formed only when 2 air masses of contrasting temperatures are converging, right? A definition of an air front, and in details we are going to do a lecture on air fronts as well in the lectures to come. So basically, this convergence is not like frontogenesis or frontal action. Why? Because remember, the trade winds, the winds on the northern side of equator and the southern side of equator, they both have similar temperature zones, so they have similar nature. So when 2 similar kinds of wind meet, then this kind of zone is very unique in itself. And that is why it is not normal like any other convergence, but it is different in nature. So the equatorial or tropical fronts are called intertropical fronts. The short form is ITF. So remember, this is an intertropical fronts or intertropical convergence zone that we say ITCZ. So this is what you have to remember, that this is a unique zone. Why? Because the nature of the convergence winds are same, and then they meet and they rise up, right? And they do not travel on surface. So this particular zone is called doldrum, as we remember, right? So this is important to remember here. Now let's look at the second belt that we know as the subtropical high pressure belt, right? It is also referred to as sometimes as horse latitudes. So this is a zone we see, this subtropical high. This particular zone is about 30 to 35 degree north and south of equator, if you see. So this is subtropical high. Now, why is it a high pressure zone? The first question is that. So remember, the winds that rise from this place, which are warm winds in equatorial zone, now after traveling to a particular location, they actually get cooler, and when it cools, it subsides, it falls down. So when it falls down, cool winds are dense in nature, they subside, and when they subside on the ground, what kind of region they form or belt they form? Subtropical high pressure belt. So that is important to remember, that this is a low pressure belt and this is a high pressure belt. So wind movement is how? From this high to the low on both sides, and this is the reason for the formation. So this belt separates 2 wind systems, the trade winds and westerlies. Now remember, if you look into this particular image, what you see, this kind of direction of these winds are the trade winds. So southeast trade winds, northeast trade winds, but just opposite side, the direction is reversed. So this particular zone is the source point or origin point, that is the high pressure belt. So the winds go in opposite directions from this particular belt. So that is important here. Now, this is also known as the source point or origin of the trade winds. That's the reason what we have observed here. So they are source of the trade winds and also the westerlies. So that is important to remember. And as we have discussed the mechanism of formation, so remember how this subsidence happens and how this high pressure belt is formed. So let's understand this process again, that what happens, how it is formed. The air, after being heated near equator, about 30 to 35 degree, this air goes here and subsides. So this kind of subsidence is known as anticyclonic circulation or condition. So wind subsides down and creates a pressure system. That is why it is high pressure. It punches down, it pushes down. So this is an anticyclonic circulation. It means if we put a weight here, if we put a pressure here, what will happen? This wind will find directions to move from within, right? So if you put a pressure somewhere, the downward wind will move sideways. So this is what happens. So this is called anticyclonic circulation, and this anticyclonic circulation is the resultant of this stability, dry conditions, and very weak air circulation as well. Now, because of this dry condition, a very peculiar thing happens here. Most of the world's major desertic conditions are found here. Remember, this was also a question sometime back in civil services examination, that why these major belts of these deserts are there. This is the reason, because they are warm and dry. Remember, as these winds, cool winds, descend down, because there is a temperature here, it is in tropics, so this again gets warm and then they disappear again. So there is nothing left for the moisture to actually gather and create clouds. So that is the reason that it is dry, and when it reaches ground, it again warms up. So there is no chance of any rainfall. So this is one of the major important points here related to this particular subtropical high pressure belt. And it is also known as horse latitude. So the reason for that is that in ancient times, the merchants had to throw away some of their horses. Remember, the technology was not like today's technology. At this particular position, the sailing became difficult. Why? Because it has a calm situation here, right? Because winds are going away from this particular location. So here it is a very calm situation, like here in doldrums. So what happens? The sailors had lots of issues in sailing their ship because of the weight. So because it was overweight, so they threw their horses, and that's how this 30-degree latitude got its name. That is the horse latitudes. Now let's look at the subpolar low pressure belt. So what we see here is this particular belt is called subpolar belt, which is about 45° north to the Arctic and Antarctic Circle in north and south respectively. So this 45° latitude to the 66.5° latitude, this is the belt for subpolar low pressure. Now the question is, low pressure is generally created because of the heating action here, right? Because the wind moves upward. But why is this low pressure created here in this particular subpolar belt? Because even the temperature is not that high. So the reason for that is it is a dynamic production. It is because of the Coriolis force, that is the force that is applied on the wind due to the movement of the planet, that is Coriolis force that we know, and the ascent of the air as a resultant of the convergence of westerlies and polar easterlies. So remember what happens here again, like in equatorial zone, what happened? Trade winds met and pushed upwards. Here westerlies and easterlies meet and then they go upward. So that is the reason why there is a low pressure. But this low pressure is rather, it's a dynamic low pressure or mechanical low pressure rather than what is there insolation based low pressure on the equatorial zone. So that is for the clarification. Now let's understand further that after this belt, what is there in the polar belt. So polar high pressure belt is the last belt on both sides as we see. So this is again a high pressure belt. Remember, this wind that goes up again falls here, subsides down. So that is again the same process, about 80 to 90° north and south latitudes. So subpolar low pressure belts after saturation becomes dry, and then when this dry air becomes cold, remember it falls on these areas, subsides down. So that is where it again creates a high pressure. Right? And in high pressure situation, again what happens? It pushes the wind, and that's why polar easterlies are formed. And easterly direction is because of the Coriolis force, rotation, deflection in this particular direction as we see. So this is the entire mechanism of polar high pressure belt formation, and it has a very low temperature that is near the polar areas that we already know. So this is the high pressure belt at the poles that we discuss.
So now, when we have discussed various facets of the temperature belts and pressure belts and various characteristics, in the sessions to come, we are going to learn more on atmospheric circulation, that is about the tricellular circulation. So stay tuned, stay safe, keep watching.